So first section we're going to look at this week, the only section, 2.4. But the first part is on what we call a phase shift. So when you graph sine and cosine, okay, let me show you what they look like. Okay. So I'm going to do the graph of sine in blue, and I'm going to do cosine in red. Okay, they have a wave pattern to them. Okay, that's sine. And cosine is pretty much the same wave. You can kind of think if you just took the blue wave and moved it to the left a little bit, it would turn into the red one. But they're both waves. When you slide a wave left or right, we normally call moving left and right a horizontal shift. Well, with trig functions, they call it a phase shift. It's the same thing as a horizontal shift. So I'm going to give you a little bit of background about the graphs of sine and cosine, and then we'll talk specifically about how do you do a horizontal shift. Okay, so we're just focusing on sine and cosine. Okay, the other graphs I can show you if you want to see what they look like. So the graph of tangent, it's not a wave. Okay, it has a pattern to it, like a repeating pattern. But it's not a graph you could draw without like lifting your pencil and then putting it back down. Sine and cosine are. Sine and cosine are what we call continuous. Tangent is not. All right, so that's a graph that we don't look at. Another one we don't look at is the cosecant and secant. So like 1 over sine. Okay, when you flip the sine, that's the cosecant. And when you flip the cosine, that's the secant. Okay, these graphs have patterns to them too. They're like U shapes and N shapes, but they're not graphs that we're going to look at. Okay. And that's the other one. Okay, so you just U shapes and N shapes again. Now, if you were to try to draw that red one, could you draw that without ever lifting like your pencil? No. So you'd have to like draw, lift it up, put it back down. So that's what we call discontinuous. All right. So we don't study these either. We just study the ones that look like waves.
So if we just have to move our pen off the paper and just go up there.
Yeah. So yeah, just sine and cosine. So first of all, sine, cosine, in fact, every trig function, they're called periodic functions. And the idea of a periodic function is it repeats itself. Okay, before I finish writing the rest, I'm gonna bring up a picture so I can kind of show you. Okay, so sine, cosine, all trig functions are what we call periodic functions. Nothing that we've studied this year yet has been a periodic function when we graph. It hasn't been periodic. All right, so let me put in just sine. And a lot of times we do zoom 6 when we set our window. We're going to do zoom 7. Okay, zoom 7 sets the window so when you graph sine and cosine, it looks good. It makes the wave a little bigger, a little bit more zoomed in so you can see it. Okay, let's look at that. And let me put that there. Okay. So I'm going to trace part of the graph. I'm going to start here. Trace like this. And I'm going to end right there. That section that I just traced in red, that's called one cycle of the graph, or one period of the graph. Basically, that section represents everything that happens. And the idea is if you take and copy and paste it, you could attach it right on the end, and it would show you exactly what the next section of the graph would look like. Okay? So if we look at just kind of the y values, kind of some of the key y values. What's the y value right there?
0.
0. How about the y value here?
1. 1.
So 0, 1,
0.
0, and then here?
1.
Yep.
0.
And 0. Those 5 y values are going to keep repeating over and over. 0, 1, 0, negative 1, 0. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Okay, they keep repeating. In order for them to repeat, you have to travel from here all the way to there. That's the distance you have to travel before they repeat. If you don't travel that far, you haven't traveled through a full cycle. Any question on that? So, when I say that the y values repeat over a given set of x values, okay, what I'm talking about is the 0, 1, 0, negative 1, 0. Those y values, and all the ones in between. I'm just naming some important ones. But those y values keep repeating over that set of x values from here to here. That's the width I'm talking about. Now, this width from here to here, it's a certain amount. If you don't stretch it or compress it or do anything to the graph, it's a certain amount of degrees or radians that you have to travel before the graph repeats itself. Does anybody have an idea or a guess how many degrees you have to travel along the x-axis before you get to the end of one cycle? Yeah?
360 degrees.
Yes, it's 360 degrees. Or what is that in radians? 2 pi. Yep. Let's write those two things down. So the length that you travel before the graph repeats itself, that's called the period of the graph. You can also call it the cycle of the graph. The normal period or normal cycle for sine and cosine is 360 degrees or 2 pi radians. Okay, so that means if I put in a graph of sine and I go to my window and I set it from 0 to 2 pi, I should see exactly from here to there. I should see exactly one cycle. So 0, 1, 0, negative 1, back to 0. Okay, that's one cycle. What if I set my window instead of 0 to 2 pi? What if I set it from 0 to 4 pi? How many cycles would I see? 2. Yeah. I'll see 0 to 2 pi. That's the first cycle. And now 2 pi to 4 pi is the next cycle. Yep. When we sketch these graphs, you're only going to have to sketch the part that's in red. Okay, we're going to sketch one cycle of a graph. Because the thought is, if you can sketch one cycle, all you have to do is copy and paste it, and then you can get the next cycle. Okay, but even though we're only sketching one cycle, keep in mind, these graphs are infinite. They go forever, left and right. We're just going to sketch a small section. Okay, so just like I showed you there, if you go beyond 2 pi with your window, all that's going to happen is the graph is going to repeat itself. Everything beyond 2 pi is going to be something you've already seen before. Just repeated. That's what makes these graphs periodic. They repeat. Now, let's say you did something like this. Put a 4 in front. Does anyone remember from when we talked about transformations? If you put a number in front of the x on the inside, does anyone remember what kind of transformation that is? Yeah?
Vertical stretch.
Vertical stretch is when it's on the outside.
Horizontal.
Yeah, horizontal stretch or shrink. And you remember if you make the number big, what happens to your graph? It shrinks it. So this is really going to shrink the graph or squish the graph 4 times as much. So if you graph that, what you've done now is you've changed the length of a cycle. You've made it cycle faster. The bigger you make this number, the faster it cycles. But if you make this number smaller, 0.5x, it's going to start to stretch the graph out. So now it's stretched out. Every graph we do until Wednesday is always going to have a cycle of 2 pi. It won't be till Wednesday that we start stretching and compressing horizontally. And this last thing, I think I already mentioned this a couple times. A period of, if I say to graph 1 period of the graph, it also is the same as just saying 1 cycle. I guess the word you use, period versus cycle, sometimes it depends on like the context. So if you're talking about like a sound wave, sound frequencies are measured in hertz. They're measured in hertz. Hertz is cycles per second. So when you talk about a sound wave, it looks exactly like it looks like a sine wave, and the frequency is measured in cycles per second. They don't really say periods per second; they say cycles. Right? And I can show you. Let me show you that. Let me go to something. So this program is an oscilloscope, software version of an oscilloscope. And what it does is it takes sound and it turns it into a picture. So the microphone's on, so it's going to pick up my voice. And there we go. So as I talk, you can see a picture of my sound, of my voice. So what's happening is the louder that I talk, that makes it go higher and lower. If I talk quieter, you won't see it go as high and low. And then depending on the frequency I talk at, you'd see a wave pattern. Now, it doesn't look like a perfect sine or cosine wave because I don't talk at the same frequency. My frequency changes, my volume changes, so it looks more chaotic. But if you were to make a certain sound, like same frequency, same volume, you could see a sine wave. All right? So can anyone, can you whistle, Cam? No? Okay, maybe whistle?
Give me a second.
Who can whistle? So when you whistle, see how it looked like a nice sine wave? It was perfect, right? Perfect sine wave. I can't whistle with a mask on either. Doesn't work. But yeah. There you go. So yeah, you see a nice sine wave. A whistle is a very simple sound, very simple picture. Human voice, pretty complicated sound, more complicated picture. All right. All right, so let me go back over here. And actually, I don't know if I pointed it out on there if it said hertz or not, but I do have another program I can show you that does mention hertz. So this program, it's not an oscilloscope. It doesn't receive sound. It makes sound. So you can put in the frequency you want to play, like 1,000 hertz. You hit start, and then you can hear that sound. So
you could copy the bell sound, sorry?
Yeah, any frequency, yeah. Any frequency sound you can copy. I mean, in theory, since I can produce any possible frequency, you could technically make any sound you want. You could make anyone's voice you want. But you'd have to know exactly the frequencies that person uses when they speak. And how they change the volume of their voice as they talk, too. So it'd be pretty complicated. But in theory, you could make any single possible sound with a frequency generator. Now, some frequencies are the same, but they sound different. Like if you play a frequency of 1,000 hertz on a guitar versus 1,000 hertz on a piano, it's just going to sound different, even though it's the same frequency, just because a piano has a different sound than a guitar. So that's another thing that would factor into a sound wave a little bit. If we could play a note from an instrument, it might not look like a perfect sine wave because most instruments, they don't sound like that, right? They have a characteristic to them that makes them sound like the instrument that they are. So the wave, it's probably some kind of wave, but it might be a little bit fancier, a little more complicated. All right, so we'll use that later on in the week. Okay, so I can do some different sound frequencies. All right, let's go back here. So you might have noticed when I said to you that the y values repeat, I named 5 what I call important coordinates. The start, the stop, the middle, the high, and the low. If you have those 5 points, you can draw a pretty good picture of a sine wave. Okay, you can't really draw a sine wave with 2 points. You need 5 to get a nice cycle. Okay, and I call those 5 points like the 5 important coordinates, or the 5 key coordinates. Let's actually put some marks on this. So if you looked at the graph, you might have noticed that there was a highest and a lowest that the graph went. It didn't go above 1, and it didn't go below -1, if you look closely. Now, we can stretch it, so it does. But what I'm saying is if you don't stretch it or you don't do anything to it, it always stays between 1 and -1. All right. And then we have these marks in here. Those are all equally spaced. So let's think about it in degrees first. If you go from 0 to 360, and you have 5 points, which means 4 sections. 5 points make 4 sections. How much is each section worth? In degrees.
90.
90, yeah. So in degrees, this would be 0, 90. 180 is the halfway point. 270 is 3/4 point, and 360 is 1 full cycle. Now, we're going to be doing it in radians. So let's write these down in radians. What's 360 degrees in radians? 2 pi. So that's 2 pi. What would be halfway? Pi. So that'd be 1 pi. What's halfway between 0 and pi?
Half pi.
Half pi, yeah, or pi over 2. And how about 270 degrees?
Three pi over 4.
And a hint would be what do you multiply 90 by to make it 270? Multiply it by 3. So what's that times 3?
3 pi over 2.
3 pi over 2. Yep. So what we're going to do now is just write down the coordinates of those green dots. Because every transformation that we do has to start somewhere. That's where it's going to start from, at least for sine. Okay? I'll put the picture of cosine on the calculator. But this is the exact picture of the first cycle of sine. Okay. So what do you think the coordinate would be for that first green dot?
0, 0.
Yep, 0, 0. Don't worry about cosine. We'll do cosine after. How about the coordinate of that green dot?
1, 1.
No, not 1, 1. Remember, those tick marks don't go by ones.
Pi over 2.
Yeah, they go by 90s if you're going in degrees. Or pi over 2 if you're going in radians. So what do you think the coordinate would be?
Pi over 2, 1.
Pi over 2, 1. Yep. That's the next one. Right. How about the green dot that's right here?
Pi 0.
Pi 0. Yep. And then the next one is 3 pi over 2, negative 1. And the last one, this point, this is really the first one of the next cycle. So the end of one cycle and the beginning of the next are the same point. Okay, so those are your 5 important coordinates for sine. Any shifting or stretching that we have to do is going to be based on that table. So, if this table is wrong, we're going to get everything wrong. Now let's get cosine. We're going to use the same x values because we know they're equally spaced. Okay, we always want to pick points that are equally spaced. That helps us to make a good sketch. Okay, so let's put in cosine. And we're going to look at it from 0 to 2 pi. And what I want to focus on are the 5 important points. So what do you think this very first point in the cycle is?
Start.
Yep, and as a coordinate, what would it be?
0, 1.
0, 1. Yep. Yep, so there's your start point. How about the next point? That marks the end of the first quarter of the cycle.
1, 0.
Well, it's going to be pi over 2 something.
0.
Pi over 2, 0. Yeah. Remember, these coordinates, these tick marks don't go by ones. They go by 90s or pi over 2s. Okay. How about the bottom?
Negative 1.
What is it?
It's pi negative 1.
Pi negative 1. Yep. How about 3 pi over 2,
0.
0. And what about 2 pi?
1.
1. Yep. Exactly. Those are the first 5 coordinates for a cosine cycle. So similar to sine, but the y values start at 1 instead of 0. So if you're doing a problem about sine, use the table on the left. Cosine, table on the right. Any question on the 2 tables? I graph sine and cosine together, and you wanted to describe the difference as a transformation, what's the difference between sine and cosine?
Cosine is horizontal shift.
It's a horizontal, yeah, one of them is, you could, depends on how you say it, but basically they're horizontal shifts of each other. Now, how far off are they from each other? Yeah?
90 degrees off.
They're exactly 90 degrees off from each other. So if I take the red one and I bump it 90 degrees to the left, it should line up exactly with the blue one. So let's take the red one. And if I want to push something to the left, do you add or do you subtract?
Or
Yeah.
from
And-
inside the parentheses out.
Yeah. And I'm doing it in radians. So I want to push it 90 degrees. So what is that in radians? Pi over 2. Okay. So now we're going to graph cosine. And we're going to graph sine bump to the left a little bit. Let's see what happens. Okay, so there's sine. Cosine. And there's the same, it's exactly the same graph now. Okay, so that shows you that sine and cosine really are the same kind of graph. Okay, just shift. And that's what we're going to study today. Shifting left and right. Okay, so now once you have the table and I give you a problem, now you have to find the 5 points on the new graph. These tables are the original graph. Now we have to adjust them. If you were to shift something up or down, what would change in these tables?
Y-axis.
Yeah, the y values would change. What if you were to shift something left or right?
The X value.
Just the x values, right? What if you were to stretch something up or down? What would change?
The what?
Just the y's. So the point is, no matter what kind of transformation we do, only one part of the coordinate will change. We're not going to do problems where I say shift it up and right at the same time. That's two things. Every problem we do is only going to have one thing for a transformation. So what you have to do is when you get the problem, okay, you got to figure out which part of the coordinate is going to stay the same. Is it the x's or the y's? And then which part of the coordinate is going to change? Is it the x or the y? Okay, and as far as kind of the background about graphing sine and cosine, that's pretty much it. Okay, so now we're going to focus on one specific kind of transformation, and that's shifting left and right. And I'll show you how to do that one. Now, if I gave you a problem where you shifted, say, up and left at the same time, then they would both change, the x's and the y's. It's not that you can't do that. It's just something in this class that we don't get into. Now, I know we're used to calling shifting left and right a horizontal shift. And you can still call it that. But generally, when they talk about it with trig functions, it's called a phase shift. Okay? You talk about shifting a wave left and right, that's the term they use, phase shift. Okay, let's start looking at a phase shift. So phase shift is when your graph is shifted left or right. whenever we do a shift, what kind of operation is it? Is it adding or subtracting, or is it multiplying?
Adding to subtract.
Yeah, whenever you do a shifting, it's always adding or subtracting. Now, if you're shifting horizontally, is that adding or subtracting inside the parentheses or outside?
Inside.
Inside. If you did it outside, that would be a vertical shift. Okay, we're going to be doing it inside. So it's going to look something like this. So it's y equals sine or cosine. And then inside parentheses, you've got to have parentheses around it. The x and the number. C is what we're going to shift by. Now, technically, you can shift by any amount you want. 10 degrees, 12.5 degrees, 14.6 degrees. But those aren't common amounts. There's 3 common amounts that we usually shift by. Does anybody have a guess what one common shift might be? Yeah?
90 degrees.
Yeah, 90 degrees. That's a very common one. Yep. Anyone have a guess at another common amount we shift by?
180.
Yep, we do 90s, we do 180s, and we also do 45s. Those are the 3 common ones. But again, you can shift by 26.3 degrees if you want to. Just not something we really do. Okay, so 2 important things when we do a phase shift, and I think you guys already know it. If you have x minus a value, which way is minus going to move your graph?
To the right.
Yes. So with x minus a value, every point shifts to the right. How much to the right? Well, depends on what some value is. And I told you it's usually going to be 90, 45 over 80. What if you have x plus a value in parentheses? Which way is that going to shift your graph?
To the left.
Yep, that's going to shift it to the left. Now, I want to start to think a little bit about what's going to happen to the coordinates in those 2 original tables. First of all, when you shift left or right, what part of a coordinate does that change? The x part or the y part?
X part.
Yeah, changes the x part. Now, if you shift something to the right, pretend like you had this point here. Let's just call that point 1, 0, and then this point here. If you shift something to the right, what happens to the x value?
It grows.
Yeah, it increases, exactly. So when you have x minus a value, it is going to shift to the right. But what we have to remember is it's backwards, just like we've learned all year. Minus a value is going to cause the x value to get bigger. That's why it shifts to the right. How about if you shift something to the left? What happens to the x value?
Decreases.
It decreases. When you move something left, the x value gets smaller. So it's the opposite of what you see right here. You might think, oh, plus, it's going to get bigger. No, when you see a plus, it moves left. It gets smaller. Okay, so we always have to do the opposite. All right, so let's write that down. So how do we figure out where those 5 points in the original table, where do they move to? Well, when we shift left and right, what isn't affected at all?
The y value.
Yeah, the y values. So as far as figuring out the new points on our graph, the y values, you can copy those down from the original table I gave you. Nothing happens to the y values. Nothing. For today. Okay, when we shift up and down, well then they'll change. But today we're only shifting left and right. Yeah. Okay, so y's are going to stay the same. Well, if the y's stay the same, then that means the x's are going to change. How do we find the new x's? So first thing you have to do is look at the problem and look at what has been added or subtracted in the parentheses. Okay, so the first problem we're going to do we have addition or do we have subtraction
Addition.
in the parentheses?
Oh, subtraction.
We have subtraction. What are we subtracting?
90 degrees. 180.
Well, you can just say
Or
it.
pi over 2.
Yeah, we're subtracting pi over 2. Now remember, subtraction is supposed to move the graph which way?
The right.
It's supposed to move it to the right. What happens to x values when they move to the right? They get bigger. So what you have to do is look at what you've added or subtracted and do the opposite of that to each of the x's. The only way that x's are going to get bigger is if you add something to them. And in this case, what would you add? Pi over 2. So you always do the opposite of what's in your parentheses. That's the same thing we've learned all year. Horizontal transformations have always been the opposite. Alright, so let's try this one. Okay, on the test, all the transformations are going to be mixed together. Shifting left and right, shifting up and down, stretching. Okay, they're all going to be mixed. So you're going to have to figure out which one you have. How do you know that that's a phase shift or a horizontal shift?
It's in the parentheses.
Okay, so two things about it. First of all, something's happening inside the parentheses. And what's happening?
Shifting 180 degrees.
Well, what operation
Uh,
do you see in the parentheses?
subtraction.
We see subtraction. Because you have subtraction inside, that means horizontal shift.
Same thing with addition.
Addition inside would also mean horizontal shift. When you have addition or subtraction outside, like that, that's going to be a vertical shift. Okay, and we'll look at that. All right. So yeah, I was just saying, when you do addition or subtraction on the outside, that's an example of a vertical shift. Okay, we're not looking at that today. Okay, when you're doing a horizontal shift, what values did we say stay the same?
The y.
Yes, y's stay the same. So I need to copy those down from the table we have. So, can somebody tell me, in the table that I just gave you, what are my y values
0,
for
1.
sine?
0, negative 1, 0.
0,
1.
1.
0, negative 1, 0.
Yep, perfect. Okay, the way this kind of problem gets graded on the test, you're going to have a table, and you're going to have a graph. You get 1 point for each x and y value you get right in the table. So the table is worth 10 points. So the table is worth a lot of points. Okay, now we need to find the new x's. The first thing, we need the original x's, because then we're going to do something to them. Can somebody give me my original x values for sine? And I'm going to write them off to the side. Yep.
0, pi over 2, pi, 3 pi over 2. 2 pi.
2 pi. Okay. So I just put them off to the side because I'm going to put all my answers in this box. That's where all my final answers are going to go. Now it says determine what has been added or subtracted and do the opposite. So look at what we've either added or subtracted, and we're going to do the opposite to all of those. So what do you think I'm going to do to all 5 of those x's? Yeah?
Add pi over 2 to everything.
Yes. And by adding pi over 2, it's going to make all the x's bigger, which means it's going to shift them to the right, and that's exactly the way they're supposed to go. So we're going to add pi over 2. The other thing is no decimals. Okay, so we're going to be writing all the x values as exact answers, usually with pi in them. Okay, so we'll start with the first one. What's 0 plus pi over 2?
Pi over 2.
Okay, so there's my new x value. Now, pi over 2 plus pi over 2.
Pi over 4.
When you add fractions, what do you have to make sure you have?
Same
Common
denominator.
denominator.
Common denominator. So if you have 1 pi over 2 plus another 1 pi over 2,
2 pi over 2.
the answer is something over 2. Yeah. So it's 2 pi over 2. And what does that reduce to?
Reduces to pi.
Reduces to pi. There's my next x value. Okay. The next one. Pi plus pi over 2. Now, how can we make pi a fraction?
Put it over 1.
Yeah, we could just put it over 1. But now you have pi over 1 plus pi over 2. Those have different denominators. What's your common denominator between 1 and 2? 2. So what could you multiply the bottom by to make it a 2?
2. Top by 2.
Multiply the top by 2.
2 pi.
So what's 2 pi over 2 plus 1 pi over 2?
3 pi over 2.
3 pi over 2. Okay. Next one already has a common denominator. 3 pi over 2 plus 1 pi over 2. Before you reduce is what? 4 pi over 2, which is
2 pi.
2 pi. Now, same deal here. Common denominator is 2. Multiply the bottom and the top by 2.
5 pi over 2.
5 pi over 2. Yep. Now, I want you to reduce the fractions the way we did. But if you didn't, you would have noticed a pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. The next one would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. Okay, it just keeps going up by 1 in the numerator. So you get 1 point for each x and y value that you get right. Okay, any questions on that? So the last part is the sketch. All right. When you label tick marks, the only thing you have to do is make sure you're consistent. These tick marks can represent anything. You can go by 5s, 10s. You can go by anything you want, as long as you go by the same thing for each one. Now, when we started out, we had 0, pi over 2, pi, 3 pi over 2, and 2 pi. Were those equally spaced?
Yes.
Yes, they were all 90 degrees apart. And we took a bunch of things that were equally spaced and we shifted them all together. So are these new values equally spaced?
Yes.
Yeah, they're still equally spaced. So what I would recommend is when you label your graph, use the x values in your table as your tick marks because they're already equally spaced. So this would be 0. 0. The first one will be pi over 2. This one will be pi. 3 pi over 2. 2 pi, and how high do we need? 5 pi over 2. So this one will be 5 pi over 2. All right, now we just graph all our points. Let me zoom out so I can see them. We've got pi over 2, 0. Pi, we're at 1. 3 pi over 2, 0. 2 pi, negative 1. And 5 pi over 2, 0. Okay, and that is our new graph. Remember when you draw it, sine and cosine waves are nice and curved. There's no sharp like turns on any of these graphs. So nice and smooth curved. Okay, the original graph would have looked something like this. Let's make a copy of that. I'll make it red. Would have looked just like that. You don't have to draw the original. I'm just showing it to you so you can see the difference. So this has been shifted to the right, exactly 90 degrees.
Nice.
That's fish. Any question on that? All right, so that was a shift to the right with sine. Well, let's try the other way. Let's do it with a cosine. Is this more of a shift or less of a shift than the first one?
More of a shift.
Yeah, more. It's double the shift. Yeah. This is a shift of 90. If you think of it in degrees, that's a shift of 180. So it's going to move twice as much. Yeah.
So technically, since they move on forever and ever in both directions, it's the same graph as the original.
You mean this? Well,
No, the side is one we're about to do.
no, it's not going to look the same as the original. If you shifted it 360 degrees, it would look exactly the same as the original. Because then it would move exactly one full cycle.
Wow. Okay.
But if you shift it pi, you're only shifting it half a cycle. So you'll see it's going to end up looking something kind of like this. That'll be one cycle. That'll be the other cycle. It's not a great sketch, but that's the idea. All right, so let's look at this. Okay, we know it's a period change because it's adding or subtracting inside. So what values stay the same?
Y.
Yep. Now, be careful. What are my y values in the original table for cosine? If you pick the wrong table, you're going to do sine instead. Yep.
1, 0, -1, 0, 1.
Perfect. Okay, so those are my y values. Just going to move that over a little bit. Now, off to the side. Don't put these in the table. Just off to the side. What are my original x values for cosine?
0 pi over 2 pi 3 pi over 2 2 pi.
Yeah. So there's my original x's. Now we have to modify them all. What am I going to do to all of those x values to move everything to the left? Because that's which way it's supposed to go. It's supposed to go to the left.
Subtract pi.
Yep, you're going to subtract pi from all of them. And we'll put all our answers in that table. Okay, some of them are pretty quick. What's 0 minus pi?
Negative pi.
Negative pi. Let's jump down. What's pi minus pi? 0. What's 2 pi? Minus 1 pi. Pi. All right, we got to figure out these other two. So we got pi over 2. I'm going to make it pi over 1. What is common denominator?
2.
2. So do it times 2 and do it times 2. So what's 1 pi over 2, take away 2 pi over 2.
Negative pi over 2.
Negative pi over 2. And same deal here, except it's 3 pi over 2 minus pi. So basically, just make that a 3. Now you're doing this problem.
5 over 2.
That's going to be pi over 2. Yep. And again, the pattern, negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and so on. And that's it. That's your table. Okay. Any questions on the table? All right. Are these x values all equally spaced?
Yes.
Of course, yeah. If you started with x values that were equally spaced and you shift them all together, they're still equally spaced. So use those as your labels. Okay, let's put those on. All right, so we got negative pi, negative pi over 2, 0, pi over 2, and pi. You don't need to label the y-axis in this case because whenever you don't label a graph, it's always assumed the tick marks are 1s. And that's exactly what my y-axis is. They're 1s. Okay. What's my first coordinate that I'm going to put?
1. Negative pi 1.
Negative pi 1. Yep. Second coordinate.
Negative pi over 2, 0.
Oh, I was a little off on that, sorry. Negative pi over 2, 0. Yep. Third coordinate?
0, negative 1.
0, negative 1. Fourth one?
Pi over 2, 0.
Pi over 2, 0. And the last one?
Pi 1.
Pi 1. Now, remember, when you draw that, it's part of a wave. Okay, so what you're really doing, there's a wave like that, you're sketching this section. It should not look like a V. Okay, it should try to make it look, as curved as you can. So kind of something like that.
Practically a V.
What's that?
Practically a V.
Yeah, just more curved. So what's actually happening right here versus right here? There's a change in what we call the curvature. This part is curved down. This part is curved up. Okay, the fancy word for that is concave down. And right at that point, it becomes concave up. And then at that point, it becomes concave down again. And then concave up again. So the concavity keeps switching. You don't have to know that fancy word, but that's what's happening. Right? Let me just put the graph back the way it was. Just like that. And that's it. That's your sketch. Any question on that sketch? Okay, so we've done a shift. One way, we've shifted the other way. We did one with cosine, we did one with sine. Let's finish up one more with sine. Okay, this will be our last one. Okay, so first thing, how do you know what kind of transformation it is?
Because it's the sign inside the parentheses.
So, and what are you doing inside the parentheses?
Subtracting.
Yep. Anytime you're doing adding or subtracting, that's always a shift. And if it's inside parentheses, it's horizontal. So this is a phase shift. Okay. What column is going to stay the same?
The Y's.
Yep. And what are my y's for sine?
0, 1, 0. Negative 1, 0.
1, 0, 1, 0. Perfect. Okay, so if you get that, you get 5 points right there for the y values. Okay. What are my original x values?
0 pi over 2 pi, 3 pi over 2, 2 pi.
Yep. Now, if you put those x values, you don't get any points for those. What I'm looking for is what's going to go in that box. Okay. All those original x values need to be adjusted. How do you shift all of them?
Opposite of what's in the parentheses.
Yep. Which in this case would be?
Plus pi over 4.
Yep. Plus pi over 4. Okay, so plus pi over 4 to all of them.
Pi over 4.
Yeah, the first one, that one's 0 plus pi over 4. We just get pi over 4. Now, you might need to find common denominators for the first couple, but then I think once you see the pattern, it'll go quicker. Okay, so let's look at the next one. Pi over 2 plus pi over 4. What's your common denominator there?
4.
4? So what would you multiply top and bottom by?
2.
2 and 2. What's 2 pi over 4 plus 1 pi over 4?
3 pi over 4.
3 pi over 4. Let's do one more with a common denominator, and then I think you'll see the pattern. Pi plus pi over 4. Okay. What's the common denominator this time?
So 4.
Same thing. So what would you multiply the bottom by
4.
and the top? Okay. What's 4 pi over 4 plus 1 pi over 4?
Pi.
Now, based on the pattern, anyone think they see the next one?
7 pi over 4.
7 pi over 4. And the last one?
9 pi over 4.
Yep. And if you were going to keep going, it'd be 11 pi over 4, 13 pi over 4. It's going up by odd numbers. Okay. Any question on the x's? Now, yeah,
Don't they have to be simplified?
that's as reduced as they can be. There's no common factor between like 7 and 4. If it was 8 pi over 4, then I would say, yes, you should reduce that to 2 pi. Now, look at the numbers that are just in front of pi. What are the numbers in front of pi all the way down?
Odd.
Just odd.
Yeah, they're just odd numbers. 1, 3, 5, 7, 9. Now, pretend you were going to put those numbers on a number line. Forget about the pi over 4 for a second. Just pretend like you're putting those on a number line. Here's 0. Okay. Where would 1 go?
Part of the 0 to the right.
Right to the right of the 0. So would the 3 go directly to the right of that?
No.
No. Where does that one have to go?
2 after the 1.
Why?
Because it goes 1, 2, 3.
Right, we're skipping. We're skipping 2. Okay, so we got 3. And then where would 5 go?
2 after.
Right, so the point in this one is we have to skip all the way through. Well, if you have to skip when you would do it this way, it doesn't matter if you put a pi over 4 with all of them. 1 pi over 4, 3 pi over 4. You're still going to do your skipping exactly the same way. That's exactly how you number your x-axis. You got to see. Actually, I could have just used that, but I'll copy it again here. So we got 0. This is 1 pi over 4. The next one is 2 pi over 4, but we don't have that one. We go to 3 pi over 4. We don't have 4 pi over 4. We have 5 pi over 4. We don't have, I need more space. I'm just going to have to go like this. I think that'll be good enough. We don't have 6 pi over 4, but we have 7 pi over 4. We don't have 8, but we have 9. That's how you have to set up your x-axis. Okay, let's do our points. Okay, what's the first point that we're going to do?
Pi over 4.
Pi over 4, comma, 0.
3 pi over 4, 1.
2 pi over 4, 1.
5 pi over 4, 0.
0. Yep.
7 pi over 4, negative 1. And then 9 pi over 4, 0.
Got a little lousy where I drew it by hand. And then 9 pi over 4 is 0. Yep. And there's your sketch. Original graph would have been there. New graph, right about there. Is there any question on that? Alright, so that's horizontal shift. Okay, so let me bring up the homework and show you what that is. It's a worksheet, okay, but it's on Schoology. Okay, so homework for each night is going to be a worksheet. So if you click on Lesson 11, 2.4 phase shift homework, click View. I think there's, let's say it's maybe about 7 questions. So 1, 2. So there's a spot on each assignment. Show me what the original graph would look like. So that would just be sine x. And then show me the transformation. Once you do the original graph for sine x one time, you can copy it for all the ones that have sine. So it's going to be the same for number 1 and 2. 3 is a cosine. 4 is a cosine. That's actually 5 questions. 5 is a cosine. Okay, in order to get full credit, you have to make sure you show the table. If you don't show the table and you just show me 5 sketches, it's going to be half credit. Okay, because the table's worth 10 points on the test. The sketch is only going to be worth like 2. Okay, so the table's worth a lot more points. So make sure you show the table. Any questions on that?